Let's just get it over with. It's the last few slides in this set, and then we can go for no, I can go for a break, and you can go for a test, right? That's how it is.
Better be talking about tomorrow.
Yes.
So you won't be here tomorrow.
I will be, but I will be enjoying myself, you know. Okay. Where were we? We discussed with you yesterday the implicit function theorem. It's not an easy theorem, especially in the full generality. You will see the statement today. It's not an easy statement. It will take you a while before you really understand what it's about. So don't expect like by the end of today you will know everything. But I'll try to comment on the slides we have. There's one or two examples. I will comment on them as well. Tutorial-wise, all of the examples in relation to the implicit function and inverse function, they will be of the same level of difficulty as we discussed today. So yesterday we discovered this with you, that if I have a curve which represents a set of solutions to an equation, and right now we do only plain two-dimensional discussion. If I have a curve which represents a set of solutions to a function, to an equation, like this, gxy equals 0, the thing is that near some points we can resolve that curve into a graph of a function. Near some other points we can't. And that's three examples on the slide. So for instance, this point, we can resolve it all the time. We can always, in principle, find a function whose graph will be the piece of a blue curve within the green box. For this point, it's not as easy as for the first point, because this box, as large as this one, within this box we don't have a solution, as we discussed it 2 days ago, because the vertical line test fails here. But as soon as we take a box a bit smaller, then we're good. We can find a function in principle, because the vertical line test is no longer failed. Now, on the other hand, the point like so, which is taken on this piece of a curve, for this point, no matter how small you make your box, the solution will never come up. The vertical line test will always be failed. And by making this three observation, we can guess now what is like how analytically we can express this condition, which ensures that a point is such that near that point we can solve. The idea is that the curve, the set of solutions, should not be vertical at that point. That's what we see from the graph. That's our conjecture we make from this experience, 3-point experience, and that is exactly what is said on the next slide. So by doing this little exercise with these 3 points, we make a conjecture, which I hope that this graph more or less demonstrates well, that the condition, analytical version of this condition, which ensures the solvability, is that the graph should not, the curve, which represents the set of solutions to an equation, should not be vertical at the point where you try to solve it. And that's how we're going to say it not being vertical, because vertical we can test with the gradient, isn't it? Because we know that if you have an implicit equation, if we have a level curve, and that's basically a level curve, isn't it? It's a set of solutions to an equation g of xy equals 0. It's a level curve. If we want to test the direction of the level curve, we have a very nice tool, gradient. So if I now frame the same analytical condition, or the same condition geometrically discovered, that the curve should not be vertical, if I frame it in terms of gradient, I will say gradient should not be horizontal, right? Curve being vertical, it's a gradient which is perpendicular to the curve all the time, is being horizontal, but gradient being horizontal, gradient it's a 2 partial derivatives, right? Being horizontal, it's a second partial derivative 0. So not being horizontal, second partial derivative is non-zero. That's my analytical conjecture, which we're going to test now analytically. So the conjecture is this: if you want to solve this, if you expecting to solve this, or if you hope to solve this with respect to y, which geometrically means if you hope to represent this curve, a set of solutions, as a graph of a function, y equal f of x, y derivative of this g function at that point should not be 0. And actually you can do it now with respect to the x as well. If you hope to solve it with respect to x, x derivative should not be 0. So your graph should not be vertical this time. Sorry, horizontal this time. So that's this slide actually gives us this analytical conjecture. If I hope to be able to solve an implicit equation, with respect to one of the variables in that equation, That's the condition which makes that possible. The next two slides, they explain why this condition works. It's basically the proof of the theorem, of the implicit function theorem. It just, in the full generality, that theorem is so difficult. I mean, it's so, like, I don't know, it's not difficult, but it's huge, you know, because it tries to cover all of the possibilities where you possibly can want to solve something. That's why the general statement is huge. But the principal idea behind the proof of that huge general statement, it's just you can explain it in the case 2 times 2. And that's why these two slides, they use the case, two-dimensional case, to explain the idea. Why this condition, derivative being non-zero, works. So let's just look into that. Here's my setup. I have a function of 2 variables, right? We have a set of points which are the level curve for that function. We fix one single point on the level curve. I call it x0, y0. It is on a level curve. That's why it is a solution, you see, to the g equals 0 equation. One single solution. I'd like to convince you that if you have this condition satisfied at this point, so if the second derivative is non-zero, and now I trace back it to the geometrical condition. If the second derivative is non-zero, the gradient is not horizontal, and then the curve at that point is not vertical. All of that equivalent to each other. So if this condition is true, then near this point I can solve. Visually, we sort of try to see this through the vertical line test, but now here's the analytical test for that. I'll just look into that. We want to show that there is a delta. So now I give you the formal statement, that we can solve it locally. So I need to convince you that there is a delta and the box of size delta around the point. So you see this is a red point in the middle, exactly in the center of my box. The size of the box is, well, double delta as a matter of fact. Delta units to the left, delta units to the right. Delta units top to the above and delta units below. I need to convince you that there is a box such that within this box, if I take the point x within this box, if I take this point x within this range from x0 take delta to x0 plus delta, within this range there will be always a point y which makes a solution. So within this range there will always be a point and a unique point which makes a solution. That's a vertical line test again, geometrically speaking, you see. I'd like to convince you that every time I draw a vertical line within this box, this line will always intersect my graph. And intersect it only once. Even though I misspoke, I said the graph, I'm supposed to say the curve, the level curve. There's no graph yet. So I will convince you that within this box, no matter where I draw this vertical line, no matter where I take this x point, this line will always intersect my curve, that's the correct way to say it, and it will intersect it once or every time. And that will be the vertical line test verified analytically, basing on these 2 conditions. That's all this slide is telling you. Now listen to the argument actually, how this condition is used there. Because somewhere in the proof, by now you had some experience in putting your own writing assignment. Somewhere in every of your assignment there must be this key step where you use the key assumptions, right? I'm not sure if every and each one of you made this key step really clear for the people who are going to read your assignment. But here I'll try to make it clear where this assumption is used, where this critical point, where this contribution of this assumption makes it possible. Right, so we're back to the same graph. Normally when people discuss this, they make this extra assumption. We just assume that this value is strictly positive. The assumption originally was that the value is non-zero. It means it's either strictly positive or strictly negative. We can just do only positive case. Negative case, it has a similar argument, right? Or you can do the negative g function, for instance. Right. Okay, so here's the first step which I need to mention. Because function is continuous and the derivatives are continuous, that's what this line says. Function being actually it's one of the things which you use in your assignment, this integral question in the assignment. I don't remember what the number of that question is. But there was a question there, like if the function is positive and continuous, then the integral around that point is also positive. That's a very similar argument presented here. The very similar idea is working here. If the function is positive at some point, and the function is continuous, the function is positive in every neighboring point as well. So you see what it said here? There's a point B, a number B, like a cutoff from the origin, such that everywhere, not only in the x0, y0, but everywhere around that x0, y0. Yeah. My partial derivative is also positive. Not only positive, it's actually separated from the zero, you see, by this number b. The other thing is, function is always, it's a min-max theorem. Function always attains its max, attains its minimum. That's why the other partial derivative, it never exceeds some number. It may be a very large number, but still there is a number which controls every possible value of my second partial derivative across this green box. That's that's another thing which comes from the continuity. Thank you. Right. Now, look what it does now, how the construction goes. The slide suggests, let's just choose a point, A0. Remember, the A was what the A was. The A was the size of that box around this point, x0, y0. It's the size of this box, the green box, across which we have this condition satisfied uniformly. This condition and this condition. At every point across this green box, we have this condition, both of these conditions satisfied. And this comes from continuity. It may be a very small box, but still we have such a box. Non-empty box, not just a point. Now, we're going to make even smaller box. And the size of that box will be A0. Yeah, we're going to make even smaller box. And then we're going to choose delta. I'm not really sure why they say less. We could probably say equal here. Well, with delta is everything is clear. Delta will be less than this number. But the choice of A0, it's still a mystery, and the choice of this A0 is explained here. Look at this. We're going to choose, let me just open everything here, but then, well, actually I know, now I see the strategy the Jonathan Kress meant to do it. We're going to choose this A0 in this way. Look at this. I'd like to make sure, I'd like to convince you that I can choose A0, still positive number, not zero number. It may be less than A, it will be less than A, but such that if I take a point A0 units above the Y0 level, this value will always be positive. Why can I choose such an A0? Look at this, what it says. It says, let's just try the mean value theorem for the G function. Mean value theorem, which is a special case of the Taylor series expansion for functions of two variables, is right here. Right? The value of my function G, the red value at any point, it is different from the value at some other point. This time I'm choosing x0, y0 by this increment. Mean value theorem, it just operates with some mysterious C and D points, but it's irrelevant actually. It's some points within this range and some points within this range. So if you take this mean value theorem, it's right here in the bottom line, then what you can say? The first term here is 0. That's the point on my level curve. That's why my G function 0, x0, y0. That's why we got 0 here. For the second term, we have control over the x derivative, right? X derivative never exceeds m. That was a condition from my previous slide. That's how I chose my box, this outer green box. That's the box within which my x derivative never exceeds m. So if I replace this x derivative with the largest possible, the smallest possible value, negative m, that will only make my expression smaller. That's why we got this sign. Now for the y derivative, we have another control. It is, let me just go back quickly. I'm using these two controls now, these two controls, in a smart way. For the y derivative, I have a control, it's positive, but it never goes lower than value number b. For the x derivative, I don't know much. All I know is that it never exceeds m in absolute value. So back here, for the x derivative, I replace it with the smallest possible value, negative m. It's a replacement. For y derivative, I replace it with the smallest possible value, but here we have much better control. It's b, positive b. Replacing these terms with the smallest possible value makes the expression smaller. That's why we have a sign. But if you compute this given this assumption, given that the delta is less than this minimum, the whole thing becomes still bigger than 0.
Question.
Yes?
What's b anyway? What is b?
It's just some number which cuts over, which just separates my y derivative from 0. It was from the slide before. Look at this again. Here.
Yeah, it says the partial derivative of y is bigger than b. Why
Yeah.
is that?
Because it's positive at one point,
Yeah.
and because this function is continuous, it's also positive in not only positive, it's away from 0 in some neighborhood of a point. It's a continuity thing.
Oh, so it has to be increasing that? Is that?
No, not really. That's the property of the continuous function. If a function is positive at a point and it is continuous in that point, then in some neighborhood around that point, function will be not only positive, it will be away from the 0 by some level, by some b. It just, well, it's a consequence of the epsilon delta definition. That's the same technique, the same trick should be very clear in many of your writing assignments, as a matter of fact. This integral question. Can I quickly open that? Unlikely. I'll show you, if it comes up, of course. It's not that. It's not going to come up.
Well, you can go through the region.
I know you can, but now I'm challenged. Probably I should give up, right? So here's my writing assignment. Here's questions. This question. Suppose h is non-negative continuous across the 0, 1, and that there is a point where function is non-zero. Prove that the integral is non-zero. If you scroll down to the hints, it's A3, wasn't it? It says, if you haven't used the continuity in your argument, then your argument is wrong. You need to use the epsilon delta to continue, blah, blah, blah. Does it say any? Oh, well, actually it doesn't tell you everything here, but it's the same idea which you used in this question as the idea which I need here.
Oh shit, I didn't even know it had hints.
You didn't even know it has hints.
I was like, oh my god.
Well, it's not a disaster yet.
Well, it's not the end of the world, but it could be.
Well, but do you? What did you say?
I struggled
You struggled.
a lot.
So, but did you? It's nice. It's nice. You see how it is good that I take challenges, right? That I not give up. But do you know that you still have a chance to submit another version of your assignment without any penalties?
Yeah, I knew that. That's why I say it's not the end of the world.
Okay.
I probably got it wrong already, but that's alright. Hints. Wow.
All right. Actually, as a matter of fact, I will open the assignments for now peer review, because it's a part of the assignment that you will need to read now the assignments of the other people and assess them according to the assessment criteria. Before I do that, I will release more hints how this assignment should be done.
Yes, please.
Now you will be able to read those. Oh, actually, there are a few videos there which I put together by Jonathan Kress from 2014. You will be able to read and watch those hints, and then use those ideas to mark the assignments of your peers. And then when time comes to submit your own, you can use those ideas to make your assignment even better, together with the feedback you're getting from your own classmates. All of that will happen next 2 weeks. That's just the highlights. But right now, probably your heads are too busy with the test tomorrow, so it doesn't matter much. But after tomorrow, it will matter. Anyway, back to the slide. So again, if you believe in these two, which is the consequences of continuity, that explains you how we come up with the fact that I can choose an a0 point less than a, which ensures that the function at the point lifted by a0 units up from the y0 level will have a positive value. By the similar argument, you can achieve the negative value if you go down by a0 steps. It's again mean value theorem. You now use the controls in a different but still smart way. You replace your x derivative with the maximum possible value plus m. and you replace your y derivative again with the minimum, or actually with the minimum possible value, but it is negative because you go down this time, so the increment, the y increment here is negative, and you get the negative value this time. And now you can make a conclusion that because your function is positive on this side, negative on this side, there must be a crossing point, because the function is continuous, there must be a crossing point, and that's the point of the solution. These two lines, analytically, they justify this vertical line test. And they work together with these two estimates on the previous slide. We pulled from continuity, and in the key assumption, the y derivative is not zero. That's right. Well, the other thing is because y derivative is positive, you got increasing function increasing if you go vertically. That's why the y value is unique. And that's why your vertical line test is satisfied. You will need to spend some time with this. It's not easy to just follow. I mean, completely understand this proof just in half an hour. In class, it took me a while when I was a student. It will take you a while as well, but eventually I hope you will see the main ideas here. Right. Well, the second thing is that the solution you will come up with from the implicit function theorem, it will be differentiable, and this is already computational part. If you want to see the derivative of the solution, all you have to do, you have to take this function, you have to sub this function into the implicit function, into the level curve equation, and just differentiate by x. When you sub it in, it is a solution. That's why it's equal 0 for every x. When you differentiate with the chain rule, that's what you come up with. First derivative of g, or x derivative of g, and then just 1, because x by x is 1. Second derivative of g, or y derivative of g, and then yx, which is f dash. If you solve for f dash here, that gives you the value for the derivative. And that's again actually here, if you look down at this expression, you will see again the importance of the major assumption. The y derivative is not 0. If it was 0, you will never be able to divide by that, because you will divide by 0. And that's the whole idea of the implicit function theorem. With some effort, you can develop this idea for functions of more than 2 variables, and in fact, not only functions, but not only one equation, but multiple equations. Look at this. Well, it's 2 examples where which explain that. For instance, if you have an equation like this, it's another level curve. We know it's a sphere. We know it's a sphere. But if you try to solve this sphere into a function, that's what you normally do, right? You just drag x and y on the other side, you take a square root, you will come up with 2 possible solutions. All of them are local solutions. If you pick a point on the sphere, on the northern hemisphere, top hemisphere, that's right, then you will take a solution with plus. If you take a point on the south hemisphere, you will take the solution with minus. If you take a point on the equator, you don't have a solution, right? Because the gradient there is horizontal. Because the gradient of this function with respect to z, with respect to variable you're trying to solve it for, it's double z, isn't it, the gradient? I mean, the derivative is double z, which is on the equator of your sphere is 0. So the conditions of the implicit function theorem is not satisfied. That's why you can't solve this sphere into a function on the equator. You can't. You can't reproduce a sphere as a function z of xy, as a graph of a function of z of xy around the equator. Implicit function theorem works here quite clearly because the gradient is horizontal, because the z derivative is 0 here. Another case which can be generalized to the implicit function theorem is the system of linear equations. If you have a system of linear equations of this type, you can solve, so you can choose a pair of variables, say yz. You can convert it into a system of equations like this, and you can solve it, right? It's a Gaussian elimination method, or it's a Kramer's method. Lots of methods you have, or some ad hoc solution. You will solve for y and z, and the solution will be function of x of the right-hand side, which carries x. And we know that it's solvable when it's solvable, when the principal matrix is doesn't have any zeros, doesn't have any non-leading columns, isn't it? Or in the determinant language, if the determinant is non-zero. Or in the matrix language, when this matrix is invertible as a matrix. That's a condition of solvability you know from the first year. If you now project this, I'll show you now the implicit function theorem in full generality. The condition which appears there, in this special case, it takes the form you know from the first year. That this matrix is invertible, or determinant of this matrix is non-zero. Yeah. So all of these cases you know, they will fit into the general statement of the implicit function theorem. It's not really an easy statement. That's why these examples, I hope they will help you to see how it works. By trying to adjust or trying to see how these examples, these three examples now, the function of two variables, general discussion, and these two examples, sphere and the system of linear equations, by trying to see how these examples fit into the general statement, it will open your eyes on the general statement. Now, listen to the general statement. Well, that's what it says. Typically, we have n equations and r variables if we want to solve. And typically, we can solve for n variables among those r. So we normally expect r be larger than n. Otherwise, like in here, you see we have two equations and three unknowns. And we expect that two out of these three unknowns can be solved in terms of the other one. The same story here. Typically, you have n equations. So already here you see how heavy the statement is. You have n equations, g1, g2, gn. And within these n equations, you have m plus n unknowns. And you can expect that you can solve for n of those unknowns. You can solve in terms of the other ones. But some conditions must be met. And that's the content of the implicit function theorem, the condition which must be met. So listen to the condition. Now it's a vector form of the same system of equations. You see, g is a bold face. That's the components of my g function. Arguments I split in two sub-vectors. X vector, that will be my independent vector after I solve, and u vector. That's a vector of unknowns which I'm going to solve for. So here's my g function, you see. I'm hoping I can find a solution, f, which depends on this m unknowns and which delivers the value of this n unknowns. I call this solution f, and I'm hoping this solution works like this. You see, if I sub it in place of u, it gives me correct numerical identity, correct numerical n identities. I should say correct numerical identities. That's the objective of the implicit function theorem. Like I said, it's not an easy theorem. It's a very heavy theorem, just the statement itself. But those three examples, if you try to feed the statement onto those three examples, that will help you to see the statement, the structure of this statement. That's the theorem itself. If I want to see the condition, before I can even state the condition, I have to consider this huge matrix, which is the Jacobian, by the way, isn't it? It's all first partial derivatives combined in an orderly fashion. All rows for each of the individual g functions, all columns for each of the variables. But I split this Jacobian now in two subparts. One of them is the part with respect to the independent variables, and one of them with respect to those I'm hoping to solve for. Now listen what the implicit function theorem says. If you want to solve it before you even start thinking how to solve it, you have to make sure that you have to make sure that, what does it say? Look at this. B x naught u naught, and the B symbol, it stands for this submatrix of this collection of partial derivatives. This submatrix must be invertible as the matrix. So it must be invertible as the matrix. If you apply this condition to the system of linear equations in my third example, this B submatrix will be exactly the principal matrix of your system of linear equations, the matrix which was 1, 2, 2, 2 or something. If you apply this condition to the sphere, this submatrix will be just one number, double z. And the invertibility of this number, double z, is when z is non-zero, when you're not on the equator of your sphere. If you apply this to my gxy example, the first example we did today, this submatrix will be 1 by 1 matrix, so it will be just number. It will be g, derivative of g by y. So every time all those conditions we saw by different methods, they all will come down to this single line. This submatrix must be invertible. And if it is, your function is differentiable. And not only that, for this function f, you can even come up with the formula for the derivative. Yeah, for this function, you can come up with the formula for the derivative. Before we look into that, I need my sip. And any questions? So if you want to see the actual value, how we can find the derivative of this function, the method actually the same as the method for function gxy. We did in my very first example today. I mean, this method. Look at this. If I go back here, this method. Oh, I press it too much. As this method, you know, when I sub it in and I use the chain rule, I differentiate it and I solve for f dash. And because my y derivative was non-zero, there was a solution because I can divide by that. The same principle will work in the general setting. Look at this, absolutely the same principle. Even though the presentation of that principle, it will be a lot heavier because the generality of the current setting is huger than generality of the other setting. Look at this, what we do. We introduce the auxiliary function h, like this. So it's a function basically which has, which takes values in m plus n, and the first m values we just take the constants. In the other ones, we take the values of the value of my solution f. The derivative of this function, the Jacobian, it has such a structure. The first m rows, they will give you the identity matrix. The other rows, the other n rows, will give you the derivative of f you're looking for. So you sub this function into your system of equations, no longer linear equations, system of equations. You look at this as a chain rule. That's the change of the view. It's a chain rule. Well, it's a composition of two functions, but now you can use the chain rule. When you apply the when you apply the derivative to this equation, left-hand side, which is 0 all the time, or here it's just, sorry, right-hand side, which is 0 all the time, in this line it becomes left-hand side, 0, but here use the chain rule in the matrix form, so it's a derivative of g function at h point, matrix product with the derivative of h. Now this shows you some structure because derivative of g, it was this huge matrix, big one, where we single out two subparts, a subpart and b subpart, and that's what is shown here. Derivative of h, it also has two subparts, identity subpart and dxf subpart, but now they arranged as a columns, or one above the other, right here. When you multiply, that's what you come up with. And now you can solve for your unknown. That's your unknown. That's your derivative you're looking for. You can solve because this factor, again, that's where the condition of the implicit function theorem works again. Because this factor, this time it's a what the heck? This time it's a matrix, but that's invertible matrix. That's a condition of the implicit function theorem. You can invert this, you can solve, and that's the solution. See? This is the inverse matrix which appears in the solution. It's not an easy statement. Don't expect it. I mean, it's a heavy statement. You need to spend some time with this before you fully understand what's happening. But trust me, those three examples, they are principal examples which every idea which is working here, it is clearly present in those three examples. If you understand the link between the ideas and the examples and in this one, that's all you need to do. Let's just see. I think I have example like, well, it wasn't a question, right? Yeah, well, I have one example, and that's the level of the examples you will see in the tutorials. I think so. I just checked it like briefly the questions in the set which I have. I think so. That's true. So look what it says. Show that there are open sets U and V containing around the point 1/2 and 1, 2, and 1/5, so that the equations define a differentiable function for which you have something like this. So basically, you need to solve these two equations, but you don't need to present explicit solution. That's the beauty actually of the implicit function theorem. Finding finding solutions to these systems of equations, if they are not linear, it's not an easy business. But finding derivatives of those solutions, it is something you can do with the implicit function theorem almost every time. So for instance, you have two systems of two equations with 4 unknowns. You can solve for 2 in terms of the other 2. So we hope to solve like this. We hope to solve for u and v in terms of x and y. This function f, finding this function explicitly, it's impossible. Let's just say it like that right now. But on the other hand, finding the derivative of this function, it is possible. Of this map, as a matter of fact, it's a map, right? It takes R2 to R2, R2 to R2. So look how we can do it. All right, to the second part of the equation, find the affine approximation to this map near the point. Well, to find this affine approximation, we need the derivative, and that's all we need. And then we can use the approximate thing. So let's just see how we find the derivative. So, this slide, it tries to structure this example to fit into the statement of the implicit function theorem. So it combines the arguments in 2 vectors, two-dimensional vectors, x, y, and y, and u, v, like this. That's the differential. That's the derivative of my g, right? It's a g function has 4 arguments, so 4 columns, 2 rows. X derivative, y derivative, u derivative, v derivative. U1, G2. We split this in 2 submatrices. First 2 columns, it's the A submatrix. Second 2 columns, it's a B submatrix. That's the splitting, you see. A submatrix, B submatrix. The value of this derivative at the point of interest, that's the point of interest, 1, 2, 1, 5, that's the value. It's a numerical matrices. My function, my equation will be solvable, my system of equations will be solvable when the B matrix, this B matrix, is invertible. That's the condition of the implicit function theorem. You look at this 2 times 2 matrix, you apply the test for the invertibility, first here tests. Do we do this? Yes, we do it here. Well, it just said here B is invertible. Oh, but it is invertible because for a matrix of size 2 times 2, invertibility is equivalent that one row is not scalar multiple of the other, right? In this case, one row is not scalar multiple of the other, very clear check. So B is invertible, so the condition of the implicit function theorem is satisfied. That's right. And that's why we have a solution, even though we can't write it up explicitly, we do have a solution locally around the point of interest. And it not only will be just solution, it will be C1 solution. And if you want to see the derivative of this C1 solution, that's the formula suggested by the implicit function theorem. You see, the inverse of B is a part of this formula. If the B is not invertible, you cannot use this formula. And that's how this formula is used. The arithmetic, you'll check it without me. And this is the differential or derivative of my function f of my solution near the point of interest, 1, 2. So if you need the affine approximation now, every component of the affine approximation now in front of you. The value of the function at x0 is here, it's u0, 1, 5. The derivative of my function f at x0 is here, this matrix, 1, 6, and times is 3, 3, 6, and 24. So here's my affine approximation. F of x0 is 1, 5, it's u0 point. Derivative of x0 right here. Derivative of f at x0 right here, and that's the increments. So if you want to find the approximate value in the point nearby, 1.2, 1.9, that's the approximate value you can come up with if you use this affine approximation. You can check whether this is any good to calculating G. I'm not really sure 100% what exactly meant by the sentence, but we can say that probably it's not of any good, because when you take the sharp point, 1, 2, and 1, 5, when you take a sharp point, G function is 0 on at that point. It's a point on my level curve. Oh, actually, that's a solution to my system of equations. It's no longer a level curve. Yeah, so by taking the neighboring point, this value will also be small. Yeah. Any questions? Most likely you don't have any, because it's not an easy task. But like I said, don't get upset too much. You need to spend some time with this. Now you have 4 examples where the implicit function theorem is used. I promise if you feed these 4 examples, or especially the first 3, into the statement of the implicit function theorem, you will see the key idea which you need to know about the implicit function theorem. There's one extra slide here which I tried to decipher this slide before I come here. I was looking at this for a while. I was thinking what we're supposed to do with this.
Is it the fifth?
Fifth?
The fifth, exactly.
Not really. It's the same function g they mean here. I suspect what they're trying to say here is this. This value, this approximate value of u and v, near the level, near this, near the solution to my system of equations, you can try to approximate this value differently. You can find the tangent, tangent subspace to the equation gxy uv equals 0 in the other method. You can find a fine approximation to the whole g function, and that here it is. That's g at the point 1, 2, 1, 5. This is the derivative of your g function, this 4×2 matrix we saw before. These are the increments. Because your function is 0, you can make this assumption of zeroness, and that will give you some system of linear equations. If you put here now in the system of linear equations your neighboring points, well, on my previous slide, one of them was 1.2, 1.9, and if you solve for the uv, that will give you the approximation, some other approximation which will be close to this. So it's another way to find this approximate value of your solution using the best affine approximation to the g function itself. Yeah, that's how I can decipher. It's still relevant. It's a good way to do it without the implicit function theorem. As a matter of fact, there is implicit function theorem here as well, because when you put here the neighboring values for x and y, and when you solve for u and v, it's another implicit function theorem case, because you're solving for something. So it's another case for the implicit function theorem, even though this time you use it in a linear case. Yeah. And as a matter of fact, you can see that the test will be identical, because if you solve here for u and v, you're going to be using this matrix 4, -1, -2, 1, which is the same B matrix used before in the implicit function theorem. So as a matter of fact, even though that's 2 different approaches, the test, the actual numerical test you have to verify, it uses the same matrix, the same B matrix in my derivative of g. Yeah, actually now I realized what's good about that. Anyway, it's not an easy task. It's not an easy subject. I'm sorry. I can ask you if you have any questions. If you have, ask any questions. I'm sure you'll have even more questions when you sit on this for a while. If you have them, ask them. I beg you, ask them. Otherwise, you will never figure it out. Or maybe you will. Maybe you will, but still, ask. Any questions? If you don't have any questions, we're basically done with the functions and differentiation. We have, not next week, next teaching week, we will discuss integration with you. But the part about the derivatives and tests attached to derivatives is done. We're gonna have tests tomorrow. I hope you will do well with the test tomorrow. Right? No? We'll see tomorrow. If you don't have any questions, thank you very much for your patience. Yeah, I'll see you. Thank you. I'll see you tomorrow.